Okay, try this again. So if you went from one minimum point to the next minimum point, again, that is a distance of 2 pi radians because you're going from negative pi on 2 to positive 3 pi on 2. That is a distance of 4 pi on 2, which is 2 pi. So that is the period of a sine function, how long it takes to go through one cycle. We can also call these graphs sinusoidal curves. It's the name given to a curve that fluctuates back and forth like a sine graph, a curve that oscillates repeatedly up and down from a center line. Okay, and then at the bottom there it says trig functions are sometimes called circular because they are based on the unit circle. So the sine function y equals sine theta relates to the measure of angle theta in standard position to the y-coordinate of the point P where the terminal arm of the angle intersects the unit circle. So we can get the graph of sine function from the unit circle. At pi on 4, the coordinates there are both root 2 over root 2. So on a graph, that comes when theta, the angle is pi on 4, so that's this point right here, pi on 4, and the value of y is root 2 over root 2, I think, which is 0.707. That's that point right there. Okay? At 0, the coordinates there are 1 comma 0. So the value of sine at 0 radians is 0. That's that point right there. At pi on 2 up here, the coordinates there are 0 comma 1. So when theta is pi on 2, the y value is positive 1. That's that point right there. At 3 pi on 4, the coordinates are negative root 2 comma negative root 2 over 2 comma positive root 2 over 2. So at 3 pi on 4, the value of y is 0.707. That's that point right there. At pi, the coordinates are negative 1 comma 0. So when theta is pi, the sine of pi is 0. That's that point right there. And we can generate the rest of the points in the same way. This gives us our graph of sine theta. It starts at 0 comma 0, and then it goes upwards to a maximum, down through the x-axis again to a minimum, and then finishes off the first cycle at 2 pi radians. So that's the graph of sine theta. The graph of cosine theta, well, we would just take the x values at each of these points. At 0 degrees or 0 radians, the cosine is 1. That's why it starts up there. At pi on 2 radians, the cosine, the x value is 0. This is this point right here. At pi, it's negative 1. At 3 pi on 2, it's 0. And the end of the first cycle, you're back to 1 at 2 pi radians. The graph of cosine is very similar to the graph of sine. What's really different is where they start. The graph of sine starts in the middle heading upwards, whereas the graph of cosine starts at the maximum. Otherwise, they are the same graph. They have the same period. One cycle happens every 2 pi radians. Okay? So we can get the graph of sine theta, the graph of cosine theta from the unit circle if we want, or we could also do a table of values if we wanted to, and just plug in numbers in our calculator. If we're working in degrees, we'd have to be in degree mode. If we're working in radians, we'd have to be in radian mode. But we've seen that the graph of sine theta between 0 and 360 degrees looks the same as is between 0 and 2 pi radians. It starts at 0 comma 0. And we saw that at 90 degrees, you're at the maximum value of positive 1. Another 90 degrees, we're back to the middle, the x-axis. Another 90 degrees, we're at the minimum value of negative 1. And another 90 degrees, we're back to the x-axis. This is one cycle of the sine function. Now, we said that every 90 degrees, something significant is happening. You're either at a maximum, a minimum, or back in the middle. We call those critical points. So the graph of sine theta has critical points every 90 degrees. That's one of the characteristics that we're going to talk about. But first, we've already talked about period. The period of this graph is 360 degrees. That's how long it takes to go through one cycle. Something else we're going to talk about is the amplitude. The amplitude is basically how high the hills are or how deep the valleys are. It's the distance from the horizontal midline, the x-axis, up to the maximum. So that is a distance of 1 unit up there, or from the horizontal midline down to the minimum. It's the height of the hills or the depth of the valleys. Those are both 1 unit. That is the amplitude of the graph. How high above the middle does the graph go? Or how low below the middle does the graph go? Yes. No. The amplitude is just 1. It's a distance. Distance can't be negative. Okay, the next thing we'll talk about is, again, those critical points. The critical points are where it's either in the middle, at a maximum, or a minimum. And they are every 90 degrees here. So we can say they're at every 90 n degrees, where n is an element of integers. You need a drink of water? We'll also do the domain and range of these graphs. Now, we only drew this graph for one cycle, but it continues forever in both directions, just repeating that pattern. There are no restrictions on what x can or cannot be, so the domain will be all values, all real numbers, or all values between negative and positive infinity. Our range, though, is different. It goes between -1 and +1. We'll also talk about the x-intercepts. Our first x-intercept is at 0. The next one's at 180 degrees, then 360, or every multiple of 180 degrees. Our x-intercepts are at x equals 180 n degrees, where again n is an element of integers. So if we're graphing it in terms of degrees, those are the characteristics that we'll be looking at. If we graph it in radians instead of degrees, it doesn't change the way the graph looks. It starts in the middle, heading upwards. Only now our critical points are every pi on 2 radians instead of 90 degrees. So at pi on 2 is our next critical point. Another pi on 2 or pi radians, the next critical point. Another pi on 2, another pi on 2. So if we start again talking about these same characteristics, only now some of these are going to be in radians instead of degrees, our period would now be every 2 pi radians to do one cycle. It doesn't change our amplitude. Our amplitude is still 1. The y scale hasn't changed, just the x scale. Our critical points, instead of being every 90 degrees, it'd be every pi on 2 radians. So n pi on 2 radians, where n is an element of integers. Remember, our critical points are either being in the middle, a maximum, or a minimum. Our domain doesn't change, and neither does our range. We're going from negative infinity to positive infinity along the x-axis. And our range still goes between -1 and +1 inclusive. Our x-intercepts will now be in terms of radians. They're at every pi radians. At 0, which is when n is 0 in this general form. When n is 1, that's pi. When n is 2, that's 2 pi. When n is -1, it'd be negative pi, and so on. Okay, so there's the sine function, whether we're dealing in degrees or radians. And you have to remember that the sine function always starts in the middle, on the horizontal midline. And we are going to be doing transformations of these graphs. We're going to shift them up and down. We're going to shift them left and right. We're also going to stretch them vertically and horizontally. We can reflect them over each axis. So we're going to be doing those same transformations that we did in chapters 1 through 3 to these graphs. But we'll always start with the base function. So if you're doing a transformation of a sine function, we're going to start with this graph first. And remember that the only difference between a sine and a cosine is that cosine starts at the maximum. So if we graph this between 0 and 360 degrees, we start at the maximum. The critical points are still every 90 degrees. So at 90 degrees, you'll be in the middle. Another 90 at a minimum. Another 90 in the middle. Another 90, you're at the maximum. So that's the graph of cosine theta. If we label our characteristics again, the period is still 360 degrees. It's the same distance to go through one cycle. Our amplitude hasn't changed. It is still 1. That is the distance from the middle to the max or the middle down to the minimum. Still a distance of 1 unit. Our critical points haven't changed. They're still every multiple of 90 degrees. Our domain and range haven't changed. Our domain goes from negative infinity to positive infinity. Our range is between -1 and +1. And our x-intercepts are a little bit different. Our first x-intercept is at 90 degrees. The next one is 180 degrees away. So 90 degrees plus 180 n degrees is a statement for the x-intercepts. When n is -1, you'll be at 90 degrees minus 180, which would be at -90 degrees. That'll be the first x-intercept to the left. So whenever we're graphing a cosine function, we're going to start with this base graph and do transformations on it. So we've talked about amplitude. It's the distance from the middle to the max or the middle to the low. But it says here, any function of the form y equals a times f at x is related to y equals f at x by a vertical stretch by a factor of the absolute value of a. This is no different than what we did before. That stretch is about the x-axis, including sine and cosine functions. If a is less than 0, then there's a reflection over the x-axis. Again, no different than what we did in chapters 1, 2, and 3. Right? But the stretch factor is the absolute value of a. So part A says on the same set of axes, graph 3 sine x, 0.5 sine x, and -2 sine x between 0 and 2 pi. So we'll start with the base graph. The base graph is y equals sine x. That starts at 0, 0. Your critical points are every pi on 2 radians. So the next one is a max, a middle, a minimum, back to the middle. So there's our base graph, y equals sine x. Now, for y equals 3 sine x, that's an a value of 3. That causes a vertical stretch by a factor of 3. All the y values will get multiplied by 3. The x-intercepts will be invariant because the values of y there are 0. So multiplying the y values of 0 by anything doesn't change them. However, this maximum point here at pi on 2, that value of y being 1 gets multiplied by 3. It's now going to become plus 3. And the minimum at 3 pi on 2 has a y value of negative 1 times 3 would be negative 3. The x-intercepts are invariant, but our max and min values are changing. Ooh, that's not good. Try that again. The amplitude is the distance from the middle up to the maximum, or the middle down to the minimum. The amplitude is 3, which corresponds to the value of a in this case. So let's see if that pattern continues by graphing 0.5 sine x. So that means that you have an a value of a half, or 0.5. That's going to be a vertical stretch by a factor of a half. You're going to multiply all the y values by a half. Again, the x-intercepts will be invariant. It's just the maximum of 1 will be half of that, and the minimum of negative 1 will again be half of that. So this is what the graph of y equals 1/2 sine x looks like. The amplitude of that graph is 1/2. Once again, the a value. And then finally, we're going to do the graph of negative 2 sine x. So here we have an a value of negative 2. That is going to do 2 transformations. It'll reflect it over the x-axis and vertically stretch by 2. We can do those two simultaneously by multiplying all the y values now by negative 2. Once again, the x-intercepts will be invariant. We're multiplying all the y values by negative 2. So a y value of 1 times negative 2 is negative 2. A minimum value here of negative 1 times negative 2 becomes positive 2. So that's what that graph looks like. The amplitude of this is 2. Remember, the amplitude is a distance. The distance from the middle to the max, or the middle to the min, is 2 units. That is the amplitude of this graph. So it asks us to state each amplitude and then also compare the graphs considering period, amplitude, domain, and range. So let's do that using a chart. Okay, we'll have our equation. We'll have our amplitude. We'll have our period, the domain, and the range. So we are going to have three equations to put in here. We've already listed all this stuff for the graph of sine x, so we don't need to do that again. Our first equation is y equals 3 sine x, and we saw that the amplitude was 3. It didn't change the period. It's still 2 pi radians. It didn't change the domain of the... It still goes from negative to positive infinity, but the range changed. Now it's between -3 and +3, inclusive. So we've got to have those square brackets there because those n values are included. If it's horizontally stretched, that will change the period, yes. But right now we're just doing vertical. The next one was 0.5 sine x. We saw the amplitude was 0.5. It didn't change the period, didn't change the domain, but the range changed. Now it goes from -0.5 to +0.5. And our last equation was y equals -2 sine x. The amplitude was 2. So what we're seeing is that the amplitude can be found by taking the absolute value of a, which corresponds to the vertical stretch factor. As we saw above, when we have an a value introduced, you get a vertical stretch by a factor of the absolute value of a. That also gives you the amplitude. Period didn't change, domain didn't change, but the range did. Remember, when you write using interval notation, it's always smaller value to larger value. So -2 to +2. So now we'll do the same for the graph of cosine. We want to do 6 cosine x, -4 cosine x, but we have to start with the base graph, which is the graph of cosine x. Cosine x, remember, starts at the maximum, which is at +1. So when we look at the scale on the y-axis here, that +1 is going to be really close to the x-axis. Our critical points are at every pi on 2. So the next one will be a middle, then a minimum, back to the middle, back to the maximum. So there's the graph of y equals cosine x. Our base graph. So then we want to do 6 cosine x. So that's an a value of 6. That means we're going to vertically stretch by a factor of 6. All the y values will get multiplied by 6. Once again, the x-intercepts will be invariant because the y values there are 0. Our starting point was where y was 1. Multiply that by 6. You'll get +6. The minimum at pi was where y was -1. That gets multiplied by 6 as well. We end at the maximum point of 1. That gets multiplied by 6. So there's the graph of y equals 6 cosine x, and the amplitude is 6. Once again, the absolute value of a. Then it asks us to graph -4 cosine x. So now you have an a value of -4. That's going to be a vertical stretch by 4 and a reflection over the x-axis. We can do those simultaneously by multiplying all the y values by -4. Again, the x-intercepts will be invariant, but all the other y values are multiplied by -4. So this +1 gets multiplied by -4. This -1 gets multiplied by -4, becomes +4. The ending point, the y value of 1 gets multiplied by negative 4. So there's that graph. And the amplitude is 4, the absolute value of A. So like we did in the last one, it asks us to compare the graphs, consider the period, amplitude, domain, and range. So we'll do this in chart form, only we don't have quite as many to do because we're just doing y equals 6 cosine x and y equals negative 4 cosine x. So that's our equation. The amplitude, we're going to do that. We'll do the period, the domain, and the range. So for 6 cosine x, the amplitude was 6. It didn't change the period. Right? This is in radians, so the period is 2 pi. The domain goes from negative infinity to positive infinity. The range will be from negative 6 to positive 6. For the graph of y equals negative 4 cosine x, the amplitude was 4, the absolute value of A. Doesn't change the period, doesn't change the domain, but the range did change. It goes from negative 4 to positive 4. Right, above, for part D, what is the amplitude for y equals 1.5 cos x? The amplitude will be 1.5, the absolute value of A. So again, the same principles that we applied in chapters 1, 2, and 3 will be applied to the graphs of our trig functions as well, including if a b value is introduced. The graph of a function of the form y equals sine bx or y equals cos bx where b can't equal 0 has a different period from 2 pi. To show this, remember that sine bx or cos bx will take on all positive possible values as bx ranges from 0 to 2 pi. Therefore, to determine the period of either of these functions, it says you can do it by solving this compound inequality. Basically, if x is between 0 and 2 pi for one full period, one cycle, if you put your b value in there in front of the x and then divide both sides by b, you'll get x is greater than or equal to 0, less than or equal to 2 pi over b. This is no different than what we did before. B causes a horizontal stretch, and the stretch factor is the reciprocal of b. So when a b value is introduced into a sine or cosine function, the period will change. It's going to be horizontally stretched. And to find the new period, you can multiply the old period of 2 pi by 1 over b, or divide it by b. And they use the absolute value symbol there because in reality that's what we do. When b is negative, it causes a reflection over the y-axis. So that's why the absolute value symbol is used. So that's really what we need to remember. If there's a b value introduced, that's going to change the period. The period will be 2 pi over the absolute value of b if you're talking radians, or 360 divided by the absolute value of b if you're talking degrees. It's also going to change the critical points. Our critical points normally are at every pi on 2, but that needs to be divided by the absolute value of b, which is the same as multiplying by the reciprocal, 1 over the absolute value of b. And if you're talking about degrees, it would be every 90 degrees divided by the absolute value of b. So the critical points will change as well. And we're going to see that in some cases it'll be easier to graph it by finding the new critical points to get your end of your first cycle, and in other words, the end of the first period. In other occasions, it's going to be easier just to use the period, and then you can work backwards to find out where those critical points are. And so we're going to see examples where one is more advantageous than the other. So again, the period, any function of the form y equals f at bx is related to y equals f at x by a horizontal stretch by a factor of 1 over the absolute value of b about the y-axis, including sine and cosine functions. And when b is negative, then it's going to reflect over the y-axis. So we want to sketch the graph of y equals sine 4x between 0 and 360 degrees. And also state the period and compare it to the graph of y equals sine x. So let's start with the graph of sine x. It starts in the middle, heading upwards. Critical points every 90 degrees. Your next critical point is your maximum. Another 90, you're back to the middle. Another 90, you're at the minimum, then back to the middle. There's our base graph, y equals sine x. Now, for y equals sine 4x, that's going to be a horizontal stretch by a factor of 1/4. So our period will be 1/4 of what it was before. Our period will be 360 degrees divided by 4, or every 90 degrees. Our critical points, normally were every 90 degrees, but now those are divided by 4 as well, which is every 22.5 degrees. And that one is hard to do here because of what the scale is. The scale along the x-axis for this graph is every 30 degrees. We can kind of estimate where they would be. Okay. So here's what we do to graph. We know the period is 90 degrees. This graph will start at 0, 0. The end of the first cycle will be 90 degrees away. So every 90 degrees, we're going to have one more complete cycle. So I'm going to put those marks on the graph right now. Every 90 degrees, you'll have the end of one cycle because the period is 90 degrees. So we've got to get one complete cycle in each of these spaces. How do we do that? Well, we can estimate where our critical points are, but here's another thing we can do. Look at the original graph. It starts at 0, 0. The end of the first cycle is at 360 degrees. What happens exactly halfway in between there? At 180. You're back crossing the x-axis. So let's change colors here, and between each of these points will be at every 45 degrees will be another x-intercept. So in between these ones at 135, in between 180 and 270, which is 215, in between 270 and 360, which will be 315. Let's go back and look at the original graph. Halfway between where it starts and the first x-intercept, halfway between 0 and 180, what's happening? You're at the maximum. So halfway in between these 2 points, we'll be at a maximum. Halfway between 0 and 45 is our 22.5, our first critical point. It's a maximum. Change colors again here. 22.5 would be approximately right there. Let's go back to our original graph. Halfway between 180 and 360 is the minimum. So halfway between 45 and 90 will be our minimum. That is 22.5 degrees past 45, approximately right there. I'm going to fill in the rest of the points by doing this halfway in between thing. It's easier with this one because of what the scale is along the x-axis. So here's our first cycle. Ended at 90 degrees. I'll do my next cycle between 90 and 180. Halfway in between there is our other x-intercept. Halfway in between these first points is our first maximum. And then halfway between the last 2 points, we're at our minimum. So here's our next cycle. Change color again. Halfway between 180 and 270 is our other x-intercept. Halfway between these first 2 points, we're at a maximum. Halfway between the next 2 points, we're at our minimum. Here's the next cycle. And for the last section, halfway between the first 2 points, I'm at a maximum. Halfway between the last 2 points, we're at a minimum. So there's the last cycle of that graph. So we've already stated the period, it's 90 degrees. And we've also stated our critical points. They're now at every 22.5 degrees, but just because of what scale we had, that wasn't probably the easiest way to get those points. Our domain didn't change, our range didn't change. All that changed was the period and the critical points. How long it took to go through one cycle changed because it was stretched horizontally. Okay? So this next one, we want to write or talk about the period. It says sketch the graph of y equals sine 1/2 x between 0 and 2 pi. It's actually partially drawn there for us. And state the period of this function compared to the graph of y equals sine x, right? Well, you've got a b value of 1/2 in this case. A b value of 1/2 means a horizontal stretch by a factor of 2. Here's the booklet. So the period will be twice of what it was before. Instead of having a period of 2 pi, it's a period of 4 pi. Because it's horizontally stretched by a factor of 2, the reciprocal of 1/2. And that fits what the graph shows. Also the critical points. Normally they're at every pi on 2, but those are also doubled. Now they're at every pi. And if we look at this graph, it starts in the middle heading upwards. The first critical point is our maximum. That's pi radians away. The next one, back to the middle, another pi radians. Another pi takes us to the minimum, another pi back to the middle. So it fits. Because our b value was 1/2, it was horizontally stretched by a factor of 2. So the period was doubled and the critical points were doubled. Bless you. So now we want to do the graph of y equals cos 3x between 0 and 360. And then cos of 1/3 x. We're just going to discuss that one because we're going to see we won't have room for it on our graph. But let's start with cosine 3x. So Here we have a B value of 3, which means you're going to have a horizontal stretch by a third. Our period will be a third of what it was before. This graph has a scale along the x-axis in degrees, so we'll talk about our period in terms of degrees. It'll be 360 degrees, 1/3 of that, or divide by 3. Our period is now going to be 120 degrees. Our critical points will also be 1/3 of what they were before. Normally they were every 90 degrees, but that's going to be divided by 3 as well. Now we're going to have critical points every 30 degrees, which for this one is going to work out quite nicely because that is the scale, 30 degrees. Let's start, though, by first doing the graph of cosine x. The base graph starts at the maximum. Every 90 degrees, another critical point. So there's our base graph, y equals cosine x. So now for this one here, our period is 120 degrees. So we're going to start at the same spot, but the first cycle will end at 120 degrees. That's the period. Another 120, which is 240. That's the end of the second cycle. Another 120, which takes us to 360. That's the end of the first cycle. Again, because our scale is in 30 degrees, and that's our critical points, it's going to be quite easy to do the rest of this. After you start at the maximum, the next critical point is in the middle. Then a minimum. Back to the middle, end at the maximum. And this pattern continues every 30 degrees. You taking off? Okay, just check out the video to get what you missed. So this is the graph of y equals cos of 3x. We've stated the new period and the new critical points that gave us that graph. Now for part B, for the cos of 1/3 x, a b value of 1/3, which means a horizontal stretch by 3. So now our period will be 3 times of what it normally was. It'll be 360 times 3. Which is 1080. So that's why we don't have room to graph it on this graph, because this graph only goes up to 360 degrees. Our critical points will also be 3 times what they were before. Instead of every 90 degrees, it's now 3 times that, so that's 270 degrees. And then part C, what is the period for the graph of y equals cos of negative 3x? Well, the negative doesn't affect the period. It reflects the graph over the x-axis. Excuse me, the y-axis. The period is still 360 over the absolute value of b. So it's still going to be 360 over 120, just like the the first example on this page. I'm sorry. It is 120 when you divide 360 by 3. The negative doesn't affect the period. That causes a reflection over the y-axis. So now you want to sketch y equals -3 cosine 2x. So we're going to combine a couple different transformations here, actually 3. So the first thing we see is that we have an a value of -3. That's going to cause a vertical stretch by 3 and a reflection over the x-axis. Then we have a b value of +2. That's going to cause a horizontal stretch by half. Our amplitude, remember, is the absolute value of a, and the absolute value of -3 is 3. That's the amplitude. That's the distance from the middle to the max or the middle to the low. The period, well, that will be, and in this case here, we are working in degrees, so it'll be 360 degrees divided by our b value of 2. Our period is now 180 degrees. So, our base graph. This is a cosine function. Yeah, we'll do that scale. So it starts at our maximum, and every 90 degrees, we're at another critical point. So this is our base graph. So what does our new graph look like? Well, we're going to vertically stretch by a factor of 3 and reflect over the x-axis. So instead of starting at +1, this graph will actually start at -3 because the y value gets multiplied by -3. And our period was 180 degrees. So at 180 degrees, we're going to be at the same point. That's the end of our first cycle. Another 180 degrees, that would be the end of our second cycle. If you look at the original graph for cosine, well, and actually our critical points, we never calculated them, but we could. They're half of what they were before. So our critical points would be every 45 degrees. Let's write those in here. So instead of every 90 degrees, they're half of what they were before, which is every 45 degrees. So we start at -3. At 45 degrees, our next critical point will be in the middle. Another 45 degrees, we're at our maximum. Another 45, back to the middle. Another 45 at the minimum. That's the end of our first cycle. Another 45. Another 45 at 270, we're at our maximum. Another 45 in the middle, and then finish off at the minimum. So this is the graph. Of y equals negative 3 cos 2x. Now it asks us for our max and min values. So they would be plus and minus 3. So let's write those off to the side here, plus and minus 3. It asks for our x and y intercepts. So our first x-intercept is at 45 degrees. And the next one was at 135 degrees, which is 90 degrees past what we started at. Another way of looking at this, the period of this graph is 180 degrees. If you look at your base graph for your cosine function, halfway in between that is 90 degrees away. And so it's kind of similar to that, I guess. But your next x-intercept is at 90 degrees from where you started from, and that pattern continues. Our y-intercept is where we started this graph at 0, negative 3. That's the starting point. It also asked us to state the domain and range. Our domain doesn't change for these ever. It doesn't matter if it's been horizontally stretched or not. That just changes how fast or how long it takes to go through one cycle. These graphs will continue in both directions, following the same pattern. The domain never changes for these, but the range does. This one goes between negative 3 and positive 3. Okay, last one. Up. Good. Okay, last one, we want to do the graph of 3 sine 4x. So here we have an a value of 3, so that's going to cause a vertical stretch by 3. It means our amplitude is 3. We have a b value of 4. That's going to cause a horizontal stretch by a quarter. So our period will be 360 degrees divided by 4, which is every 90 degrees. Our critical points at 90 divided by 4, which once again is our 22.5 degrees. And based on what our scale is, it'd probably be easier not to use the critical points to get our points, but to talk about where it starts, where it ends, what happens in between there, and so on. But this is a transformation of y equals sine x. So that's our base graph. Sine starts in the middle, heading upwards. Our next critical point, we're at our maximum of 1. Back to the middle. Minimum of negative 1, back to the middle. So there's our graph of y equals sine x. So for our graph, we're going to start there but our first cycle will end at 90 degrees. And then another 90 will be our second cycle, then our third cycle, then our last cycle that we have room for on this graph. If you go back to the original graph, it starts at 0, ends at 360. Halfway in between those at 180 is another x-intercept. So the same thing will happen here. Halfway between these 2 points at 45 degrees, there's another x-intercept. Halfway in between. Halfway in between these first 2 points now is our first maximum, which will be at positive 3. So there's 1, 2, 3 is up here, and negative 3 down there. So approximately there, that's where 22.5 is. Another critical point, you're at the minimum. Another 22.5, or middle. Another 22.5 degrees, you're at the minimum, back to the middle. Maximum, middle, minimum, middle. Maximum, middle, minimum, middle. Maximum, middle, minimum, middle. So the graph would look something like that. Our amplitude is 3. We've already stated our period above there. It's every 90 degrees. Our maximum values are plus and minus 3. Our x-intercept. Our first one is at 0. Our next one is 45 degrees away, and every 45 degrees after that. So we can state our x-intercepts at 45 n degrees, where n is an element of integers. Our y-intercept is at 0, 0. Our domain goes from negative infinity to positive infinity. That's never going to change. Our range in this case between negative 3 and positive 3, because our amplitude is 3. So questions 4, 5, 7, and 8 on page 233 to 234. We'll do those for practice. So next week we'll look some more at transformations of the sine and cosine functions. Yes, ma'am. Yeah.